Okay, today we will discuss new topic, which is the Sakata model. So, in the last class, we discussed about different uh, techniques associated with the detection of extremely short-lived particles, and more such particles were discovered. More particles were added to the list of particles, and it was necessary that when the number of particles increased, they had to be classified into in a certain ordered manner. Then only we can easily analyze all those particles with the different properties. So here more and more, since more and more particles were discovered, classification of those particles becomes necessary to have an order. And initially, those hadrons were classified into baryons and mesons. So more and more particles were discovered. discovered. And it was was necessary to classify them in a particular order. So initially, the classification were performed for the case of um, that hadrons were particles discovered, and it was necessary to classify them in particular order. And initially, hadrons hadrons are were classified initially hadrons were classified as into the baryons and mesons. So the first classification was like these hadrons were classified into baryons as well as mesons. Okay. Then in 1956, Japanese scientists in so this in 1956, Japanese scientist yes Sakata Sakata proposed a new model, a new model called Sakata model. And in this model, which classifies all hadrons in terms of uh, neutron, proton, and lambda zero. So, in this particular model, he proposed with this Sakata model, and according to this model, according to this model, all hadrons, all hadrons are composed of all hadrons are composed of combination of six non-particles, non-particles, which are neutron, proton, and lambda zero, and they are antiparticles. They are antiparticles. So these six particles are neutron, proton, and lambda zero, and they are antiparticles. So total number is six. So in Sakata model, all hadrons, all hadrons are composed of. Uh, he 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 proposed this model in such a way that all hadrons are composed of combination of six known particles, and those six known particles are neutron, proton, and lambda zero, and their antiparticles. So the combination of these six particles, neutron, proton, lambda zero, and their antiparticle, will form all the hadrons. Okay, so he made it like the hadrons, all the hadrons are composed of the combination of these six known particles. And this particular group we can see from here. One table. You can see from here this table. The mesons, according to the Sakata model, mesons, you can see from here. Here we have pi 0, which is pi meson, and pi plus and k plus, k mesons, kaons, and pions. These are pi minus. Here again, here mu 0. You can see this is kaon, which is minus, k minus, k minus, and k0 bar, antiparticle of that k0, and it is. So all these are formed with the combination of for example, first case we have proton and this antiproton combined together to form this phi 0 and eta 0. Similarly, here this neutron, anti-neutron, and this proton, which are combined to form this particular phi plus. Similarly, if you consider this lambda 0, this lambda 0 and this proton, this one, which are combined to form this K minus. So this is the Sakata model, which says that the hadrons or the hadrons are composed of combination of these six particles, neutron, proton, lambda zero, and their antiparticles. So these six particles, using these six particles, you can have all those hadrons by using the Sakata model. So combination of these six particles will give you the particles, the hadrons. Okay. Now, if you consider the quantum numbers associated with this model, we can see this is P bar, this one, is antiproton. This is proton. So these two combines together to form this phi 0 and eta 0. Okay, so we'll just size. Okay, so this will form this this proton and this antiproton will form this pi 0 and eta 0, and we can see this proton is having baryon number which is equal to 1, the charge is equal to 1, and I3 is equal to 1 by 2, that is isospin equal to 1 by 2. This antiproton which is having baryon number A which is minus 1, charge is also minus 1, and the isospin is also minus 1. Okay. So combination of these two, if you consider, we will get 1 plus minus 1, that is 0. You can see from here A equal to 0. Minus 1 plus 1, that is also 0. Charge is 0. And I3, here it is half, here it is minus half. So I3, combination of that will give you I3 equal to 0. So such a particle with baryon number 0, charge 0, I3 0, that is phi 0 and eta 0. Let's take another example. Consider this lambda 0. Color. Consider this lambda 0 and this, let's say, take some other. Let's take this p bar. So these two will form these two. These two will form this k minus. These two will form this k minus. So that will be coming like if you consider this baryon number which is 1 for lambda 0 and charge which is 0 and I3 also 0 for lambda 0. You can calculate it by using that formula that we discussed earlier. And this p bar which is having baryon number which is minus 1, we already discussed that, and charge which is minus 1, and I3 is also minus 1. So combination of that, baryon number is 1 here, here it is baryon number is minus 1, so total baryon number is 0. Then Q is equal to 0 here, Q is minus 1 here, so total charge is minus 1. I3 is 0 here, I3 is minus half here, so total I3 is minus half. Such a particle with this combination, A equal to 0, Q equal to minus 1, I3 equal to minus half, which is K-meson with the negative charge. Okay. Similarly, all hadrons we can form all those hadrons by using these 6 known particles, neutron, proton, and lambda, and their antibody. So this was the model which is proposed by Sakata, which is known as Sakata model, which classify the hadrons as a combination of these 6 particles. So he also explained the composition of non baryons, like what we discussed for mesons, using that neutron, proton, and lambda 0 and their antiparticles. As similar to this is for mesons. Similar to this, he also proposed um, composition for baryons. The for baryons also he proposed by using these 6 particles. Okay. By using the same 6 particles, he also explained or proposed a composition for baryons also. Okay, this is for mesons. What we discussed about in this table is all those particles which are meson, pi mesons and k mesons, and uh, eta. So these are mesons for this table. This is meson, but he also explained the same kind of compositions with the neutron, proton, and lambda zero and the antiparticles for baryons. Okay, so whole hadrons he explained. We only discussed about those mesons. Okay. So there were some difficult predictions in the Sakata model. For example, you consider there were some difficult predictions by Sakata model, because when you consider, for example, let's say mass of mass of for example, if you consider this, if you consider proton and proton annihilation, proton and antiproton uh, uh, interaction, for example, having total mass of 1,876. So consider uh, like proton, antiproton having having mass of 1,876 mega electron volt, producing producing pion of mass 135 mega electron. Okay. Consider this scenario. We have proton and antiproton, and which are having mass of a 1,876 mega electron volt. But a combination of that will produce a pion, okay, a pion of mass 135 mega electron volt only. Okay, so that is not that much good concept, because here we have more mass 1,876 mega electron volt, but here it is only 135 mega electron volt. So there is a very big change. The change is very large. So that was not that much acceptable at that time. If you consider the mass of proton and antiproton, which combine and form a pion, which is having mass only 135 mega electron volt, that was not that much easily accepted. Okay, so there were some mixed response for this Sakata model from different scientists. Some accepted this model because it is explaining somehow the combination of different hadrons, different different particles, proton, neutron, and lambda zero, which will form those hadrons. That was okay. So some scientists was okay with this model, but some of them were not that much satisfied because of some difficult predictions or some predictions which were not that much easily acceptable. Like in this particular case, which is proton and antiproton, which will be having a mass of 1876 mega electron volt, which is producing a pion of mass 135 mega electron volt only. That is not that much acceptable. So such kind of difficult predictions were there in Sakata model, so that it was not that much acceptable in all the scientific community, but some of them have agreed with it because of his idea of classification by using the composition of these neutron protons. And later, another model, which is known as the eightfold way, is known as eightfold way. The eightfold way. Just check that in this eightfold way, this was proposed by Zellman and Niemann in 1961. So this is in 1961 by Zellman and Niemann. Uh, in 1961, Zellman and Niemann proposed this model. This model. And they classified the hadrons, all those hadrons again, into families or super multiplets using the mathematical group concept. So what they did, they classified hadrons into families or super multiplets, using the mathematical group concept. So by using this mathematical group concept, they classified those hadrons into different families or super multiplets. Super multiplets or different families. Families means different groups, you can say. So by using this mathematical group concept. Okay. So what is that multiplet? So multiplet means if you are having these multiplet members, multiplet members, multiplet members have same spin, baryon number, then strangeness, then and isospin. So this family or multiplet members have same spin, same baryon number, same strangeness, same isospin. All those, if there are particles with the same spin, same baryon number, same strangeness, same isospin values, then they are classified into a one single family. They are single family or a multiplet. Okay. So they are multiplet. So those multiplet will be having same spin, same baryon number, same strangeness, and isospin. Okay. And if you consider that super multiplet, another one, if you are having super multiplet, then this super multiplet will be having same one will be having same spin similar to that multiplet and baryon number. These are super multiplets and baryon number and parity. So if the particles which are having same spin, same baryon number and parity, they are called as super multiplets. So those group of particles which are having same spin, same baryon number and same parity, and they are super multiplets. If they are having same spin, same baryon number, same strangeness and same isospin, but different parity, but they can be classified as if these four are same, then it is called as multiplet. Okay, these are not super multiplet, but they are multiplet. So just as the particles of multiplet can be regarded as different states of a basic particles, particle in isospin, then as for particle in super multiplet, they can be regarded as the different states of basic particles in unitary spin. Okay. So just as the particles, for example, in this case multiplet, all those particles can be regarded as different states of basic particles in isospin. So if you consider the isospin case, this particular case, if you consider different set of such values, for different set of such values, I will explain this by using that model. I'll just write it here. This sentence. So just as the particles of multiplet can be regarded as different states of basic particle in isospin. I will just explain this later. Then particles in super multiplet can be regarded as different states, different states of basic particle, different states of basic particle, different states of basic particle in unitary theories. I'll just show this. So, for example, if you consider an octet, an example for multiplet, we can consider as an octet. Okay, so in that octet, this particular octet means 6 particles we can see from here. This particular geometry arrangement, you can see here is, and each of this set consists of total of 8 number of particles. You can see here there are 1, 2, 3, 4, 5, 6, 7, 8. So these are octet. This is an octet of semi-stable. This one is sigma semi-stable baryons. These are example for octet. This is an example for octet of semi-stable baryons. Neutron, proton, sigma minus, sigma 0, sigma plus, lambda, lambda zero. And this one is cascade or psi particle, psi minus and psi 0, or cascade minus and cascade 0. Okay. So this is an example for multiplet or a family of particles. And you can see from here, these particles which are arranged in such a way that this axis we are having strangeness on this axis. Here we have strangeness. So this is your S values. And on this axis, actually we are having the I3 values. So Z component of I3. These are the Z component of I3. Okay. So this sigma plus will be having Z component of I3 which is equal to 1, and this cascade is having 1 by 2, and this one is at the center, and this one will come over here with the spin I3 equal to 0. Then we have minus half, then after that minus 2. This is correspond to this minus 2. Okay. So these are I3 values. And these are strangeness. This is S equal to 0 and S is equal to minus 1, S equal to minus 2, like that. This is 0, minus 1. So this particle, sigma minus, is having strangeness of minus 1. This particle is cascade minus and cascade 0, which are having strangeness of minus 2. Okay. So this is an example for that multiplet. And you can see these are having same isospin values. If you consider this particular group, they are having same values is equal to 1. But their I3 components, this group if you consider, they are having same I, that is isospin, which is equal to 1. But their I3 will be minus 1, 0, and plus 1. So that will be different. So with that value I3, we can classify them, or we can distinguish these particles, sigma minus, sigma 1, in this particular classification is the eightfold way, and this is correspond to the values. Similarly, you can classify neutron and proton. They are having different I3 values. and this will be having I which is equal to, this group will be having I which is equal to half. So these are multiplet members. Okay, these are multiplet members. They are having same strangeness value, s is equal to 0. They are having same baryon number. These two are baryons, so they are having same baryon numbers, and they are having same isospin I which is equal to half. Okay, and they will also be having same spin which is half. A spin, baryon number, isospin, and the strangeness, they are same for all these groups. If you consider this neutron proton, they are having same, all these values same. If you consider sigma minus sigma 0, sigma plus, these are having same isospin, strangeness. You can see from here s is equal to minus 1 for all these particles, and they are having same spin, same baryon number also. And here also you can see they are having same strangeness, isospin, and all other values. So these are multiplets. These are the multiplets. This is a doublet. You can see this is also a doublet. This is a triplet. A triplet. One is triplet. These two are doublet. In neutron and proton, which is doublet. Two particles are there. And this center one, sigma 0, sorry, this lambda, this lambda, this lambda, this one is a singlet. One is singlet. Okay, this one is singlet. So these are different multiplets or the families of particles. Okay, and if you consider super multiplet, they will be having same spin in the same way. They will be having same spin and baryon number and parity. So if you consider these particles which will form an octet will be having baryon number which is equal to 1, because these all these particles have baryons, neutron, proton, cascade, sigma, all those particles which are having baryon number which is equal to 1. Okay, they are having same spin. If you consider that spin value, and if their parity also which are okay, then this set of values will form a super multiplet. Okay, this will form a super. So this is also again super multiplet octet of semi-stable baryons. But if you consider here, uh, in this particular case, you can see from here. So this is another example, which is also an octet. This one is an octet. Write it below. This is an octet. Octet of semi-stable. What are these? These are mesons. These are mesons. So in this case also your baryon number will be same, because baryon number is 0 for meson. So all these mesons will be having baryon number which is equal to 0. Okay. So they all of this will be these particles. This is a super multiplet if you consider them as a whole, as an octet. So this will form super multiplet. And this side, as we discussed, we are having that strangeness, and on the other side we have spin. Yes, I will just paste this one. So this three values. This side we will be having that I3. So this is I3, and this is your strangeness, the y-axis, your strangeness. So strangeness equal to 1 here, 0 here, and -1 here. And we'll be having I3, which is for 5 plus, which is particular case. We are having I3, which is equal to 1. And here for K 0 bar and K plus, this is applicable for both. For only one particle. For both, we are having spin, which is equal to plus half. Then we have 0. At this point, have 0. I3 is equal to 0. Then we have minus half for K minus as well as K0. Both of these. We have minus half, and then we have minus 1. Here it is minus 1. So this is I3 values. This is strangeness value on the y-axis. So this again form another octet, which is a super multiplet. So what is the baryon number here? So the baryon number A for this particular super multiplet, this particular octet or super multiplet, that will be 0. And then we have a spin, which is also 0 for these particles, spin equal to 0. And then we have parity of these particles, the set of particles, which is equal to -1. Parity will be equal to -1. So all these particles, which is K1s, this K0, K plus, phi 0, phi minus, K minus, all these particles will be having same baryon number, which is equal to 0, same spin, which is equal to 0, same parity, which is equal to -1. So they form a multiplet, okay, super multiplet. Consists of, so this one consists of 4 multiplets. So you can see this is a doublet, and then after that we have this triplet. You can see this is a triplet, 3 particles. This is again a doublet, okay, and we have a singlet. So there are 4 multiplets. Okay, this one is a multiplet. This is a doublet. Already that. This is a triplet. There are 3 particles. Triplet means multiplet with 3 number of particles, and that triplet will be having same strangeness, baryon number, same spin, and the isospin also for triplet case. That's for multiplet case. When you consider super multiplet, they will be having same baryon number, same spin, and same parity. Okay, so all these particles are forming a super multiplet, which is an octet, and in that super multiplet we have different multiplets, which are doublet. This one is doublet. This is triplet. This one is singlet. There's only one particle in this particular multiplet group, and this one is again a doublet. So there are total of 4. In this particular case, we are having 4 multiplets. And these 4 multiplets will form that super multiplet, which are having same spin, parity, and baryon number. And I forgot to say that this particular angle, if you consider this angle, if you consider this angle, if you consider this one, which are having a charge of -1. Okay, and if you consider next particles like this particular line coming like this will be having charge which is equal to 0, and this particular one which is coming in this line will be having charge equal to q equal to 1. This is q equal to 0, and this is q equal to 1. So K plus phi plus they are having charge which is +1, so they are coming in this line, and the other particle which is coming in this line will be having charge which is equal to 0. So K0, phi 0, and K0 here, K0 bar, this one is K0 bar, and this eta. All these are having same charge which is equal to 0. The same scenario we can observe in the case of baryons also. So I will just erase this. Right. So, so you can see from here this particular one, this direction, this line you can see this is having q equal to +1, q equal to 0, and q equal to -1. So this sigma minus and cascade minus will be having charge -1, neutron sigma 0, this lambda 0, this psi 0, cascade 0 will be having charge 0. So all those particles which is coming in this line will be having charge which is equal to 0. All the particles which are coming in this line which are having charge which is equal to -1. So that also you notice. And here, what is the condition for this super multiplet? That is the octet. So that is baryon number here. Baryon number is 1. You know, all these are baryons. This is an octet for semi-stable baryons. So all these particles are baryons. So their baryon number will be 1, and their spin will be half. All these particles will be having spin half, and their parity equal to minus, sorry, in this case it is +1. For baryons it is +1. So their parity will become +1. So this is the group. So they are having same baryon number, same spin, same parity. So this will form a multiplet, super multiplet, which is the octet that we just formed. From a super multiplet, and that is nothing but that octet, this particular octet. And in that octet or in that super multiplet, we have different multiplets. This is doublet that I already discussed. This one is triplet, this is singlet, and this is again forming doublet. Four multiplets are there in this case. Four multiplets for this super multiplet. Okay, so that's about baryons. And if you further consider the case with mesonic uh, resonances, we have different resonances, mesonic as well as baryon resonances. So if we consider in this first case, we are considering baryonic resonance. And this particular super uh, multiplet, which is known as decouplet, this is called as decouplet. So this is a decouplet. So this particular form, this is not an octet. Okay, this is a decouplet. Okay, so how many particles are there? This 4, 3, 2, 1. So total 10 deca. So this is a decouplet. Decouplet. There are 10 particles. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a decouplet of baryonic resonance. Why it is baryonic resonance? Baryonic resonance. So why it is baryonic resonance? Because all these particles are baryons, but they are not the actual baryon particles, but they are resonance particles, which means they are the extremely short-lived particles. So these are baryons, but they are resonance particles. They are extremely short-lived particles. Okay. So in this particular case also, we will be having strangeness on this axis. I will just put one line here. That. Okay, so this axis is strangeness, and in this axis, just here. Okay, so here in this particular axis, we will be having strangeness as discussed earlier. So here we will be having strangeness. So this point strangeness is 0. And at this point it is -1. So always remember that it is coming 0, -1, -2 like that. +2, -3. It's not going to be plus for a single part. Okay? It can be plus, but not for this case. Remember those strangeness values in each case. For example, in this case, we have that +1 condition. Okay, so here it is 0, -1, -2, -3 for baryons. Talking about these baryons. So it will be always 0 minus values for the case of baryons. Okay. But in the case of mesons, if you consider the previous case also, it will become positive. You consider here for the case of mesons, you can see this one is equal to positive 1, then 0, then minus. But in the case of baryon, it will not become this positive. So this is decouplet. This particular group is called as decouplet. It will be having a structure like inverted pyramid. Okay. So that structure being known as decouplet, and it will be having 10 number of particles. You can see. And this is another super multiplet. So in this super multiplet, we will be having this is a this will be having 4 particles. Okay, this particular one is 4 particles, and if you consider that this is quadruplet, I don't know what is exact for this particular case, but this will be having 4 particles, and this will be having 3. This is a triplet, and this one is having this is doublet, and this one is and this so this will be having total 10, and with how many 1 2 3 4 multiplets again, 4 multiplets, that will form 10 particles, and those are having strangeness 0 -1 -2 -3, and here we have the charge is that line which is coming like this, as we discussed earlier. So this will be having +1 charge, this will be having charge which is equal to 0 line, and this line will be having charge which is equal to having charge equal to -1. Okay, and here we are having that spin value, that is I3 component. So for delta plus plus, we will be having the I3 component this quadruplet one will be having 3 by 2. This delta plus plus will be having I3 which is equal to 3 by 2. Then the next one is sigma plus plus will be having value which is 1. Then we have this one, right? And this one also. These both are coming in the same line. So these two are having 1 by 2 of spin I3, that is Z component of that isospin will be 1 by 2, then 0. Then we have -1 by 2 and -1, -1, -1. Then after that we have -3. So this is the I3 component or isospin, Z component of isospin for different cases of this this particular multiple decoupled. Okay, this is for baryonic resonances or baryonic extremely short-lived particles, baryons. And if you go for the same for mesonic resonances, so this we already discussed. This side we have already discussed in the case just before. And here we have the resonances. These are K star 0, K star plus. Okay, so these are resonance particles or extremely short-lived particles. These are rho minus and rho 0, rho plus. These are extremely short-lived particles. And again K star and K star 0 bar. And this is minus. K star minus. And this K star minus. Okay, so these are uh, this particular group I am saying. So these are mesonic resonances. Mesonic resonance. Okay, these are mesonic resonance. What is this? This is not a decouplet. This is not a decouplet, but this is an octet. Okay, you can see 8 particles here. So this is again forming another octet of mesonic resonance. You can see from here. These are mesonic resonance, which will form another octet with the rho particles, counts, and this omega and phi. Okay, so this is another example for an octet, which is nothing but the mesonic resonances. So these are not counts, normal counts. These are extremely short-lived counts. That's why we put K star here. So they are extremely short-lived particles. So this one is plus. This one is minus 1. This one is minus 1 for strangeness. And all other values you can see this is I3. So this should be 3 components. This is I3. This we already discussed. This group we already discussed before for mesonic case, octet of semi-stable mesons. And here we have octet of our mesonic resonance. And this one will be having minus half. One also will be having plus half between that I3 values. So this is the set of mesonic resonances which is forming an octet. So all these are the classification which is done under that eightfold way. Okay, but so under that eightfold way, we are having all these classification. Okay. Now I will give you some important fact about this eightfold way. So in this eightfold way, what they have done, so they form an octet. So all these particles form an octet, and in Si3 plane. Okay. So in the first two cases, if you consider all those particles form. I'm talking about that first two cases, or for those octet cases. So that semi-stable mesons and semi-stable baryons. Consider an octet of those cases. So all those particles form octet, which are octet symmetry in Si3 plane. Si3 plane. What is that? Si3 plane means on the y-axis we are having that strangeness, x-axis we have I3, so that plane will be Si3 plane. And Gell-Mann and Niemann, another point is that Gell-Mann and Niemann suggested that suggested that strong interaction will be invariant under three-dimensional special unitary group and is said to have SU3 and it is 3D special unitary group and it is said to have SU3 symmetry. So if you consider that strong interaction, this strong interaction, I guess this Gell-Mann and Niemann suggested that this strong interaction will be invariant under this 3D special unitary groups. So, and it is said to have that SU3 symmetry. They will be having that SU3 symmetry. And further, if you consider the success of eightfold way, success of eightfold success of this eightfold way. I will just show some of them. So first one is in 1961 only that 7 semi-stable mesons were known. Both Sakata model and eightfold way predicted the existence of the particles eta zero. Okay, so I will just write it very shortly. So this is in 1961 only 7 semi-stable mesons were known. Both Sakata and eightfold way models predicted the existence of eta zero particles. So in both cases, this was a successful thing because these eta zero particles were not known at that time when they proposed these models, but later it is found that this particle is it was discovered. Okay. Then it's discovered. So first eta zero was this eta zero particle were uh, successfully predicted by these models, Sakata model as well as eightfold way. And this is a success for both those models. And in another case, we consider the eightfold way predicted the mass of particle 570 megaelectron. Later it was discovered that almost with the same. So in this particular case, the 8, I will just put EF, eightfold way. So this eightfold way predicted mass of this particle as 570 megaelectron volt, and later it was discovered with the same properties. So I'm just writing it the same property. So some other properties also predicted by eightfold way. So all those properties were also true. Later it was confirmed. Okay. So one of that property is that 570 mega electron volt of mass for that particular particle. So that was later discovered. Those particles were later discovered, and it is confirmed that whatever the mass predicted by the eightfold way was true, and also other properties also, which was also predicted by the eightfold way for that particular particle were true. So it is another successful story for this eightfold. And the another important success, which was also done by this eightfold way, is that the contradiction. If you consider that the contradiction between eightfold way and the Sakata model, by using that Sakata model, we have having this sigma psi particle, these two particles, psi 0 and psi minus, psi 0 and psi minus, or cascade 0 or cascade minus. So these particles, which was unknown, these two particles were unknown, and these two particles were predicted by the Sakata model, which are having a spin of 3 by 2. So in Sakata model, which was predicted as spin equal to 3 by 2, but in eightfold way, this one was predicted, this cascade 0 and cascade minus, they were predicted with the spin half. Okay, in eightfold way, they were having spin half. So this is the difference for the Sakata and eightfold way. The proposal of Sakata and eightfold way were different for these particular particles, the psi particles or cascade particles, because in Sakata model, it was predicted that this psi particle or the cascade particle, they are having spin which is equal to 3 by 2. But in eightfold way, it predicted that these particles, which were unknown at that time, are having a spin of half, a spin of 1 by 2. And later experimentally, it is found that they are having spin is equal to half. So experimentally, this was correct. Experimentally, is verified that cascade 0 and cascade minus as having spin half. So this one later, which is verified. Okay, initially it was not known. So in it at that time, this one was true. Eightfold way successfully predicted those spin value, but the Sakata model failed for this particular scenario. Another important success of this eightfold way is the discovery of omega minus or prediction of that omega minus particle. Okay, so another important success of eightfold way is the prediction of omega minus particle. Omega minus particle. The prediction of this omega minus particle was another important success of the eightfold. Why it is that much important? Because initially it was not there. Okay, and if you consider that delta family cannot be accommodated in octet because it is 8 number. It is having if you consider that delta particles. Okay, if you consider that delta particles, this delta particle, how many are there? There are 4 number of delta particles. Okay, delta plus plus, delta plus, delta 0, and delta minus. So this will never form an octet. That is sure, because an octet will be having this kind of structure. So they can have a maximum of 3 in this particular scenario. For a multiplet, they can have maximum of 3. So these particles never form an octet. Okay. Then it was thought that the possibility for a super multiplet of 27 members. Okay. For example, if you consider we are having something like this, there are 4 particles at the center, and then 3, then 2. Uh, let, let me see how it will come. So this one will form 10. Okay, but we need this. So if you're assuming it is like this, uh, this is these are the there should be 4 particles. Sorry, so the drawing is not that much good. So, but if you are considering same kind of scenario with 27 number of particles, so that these delta particles can be accommodated in that particular group. These 4 particles can be accommodated in that particular group. But that was also not that much easy. That was not possible. But later experimentally it is found that these 27 super multiplet resonance particles failed, and Gell-Mann and Niemann predicted that this should form a decouplet. It should form a decouplet. But what was the problem with this particular case? So if you consider that decouplet case, you can have this 4 delta plus delta 0. You check that the order. I'm not just writing here. I don't know whether it is in the same order. So this one is delta minus. So only one minus will be there. I will just check that order. Okay, this one is delta minus, right? So this one is delta minus. This side, this is delta minus, and then we have delta 0, delta plus plus. Then you have that sigma, okay, sigma star. This one is sigma stars. Sigma star minus, sigma star 0, sigma star plus. Then we have that cascade star 0, cascade star. So this one is 0, this is minus. And then actually this omega were not there. This omega was not there. So they predicted there should be another particle here. This one is omega minus. They predicted this particle should be there, and they also predicted all the properties associated with this particular omega minus. But this omega minus were not discovered at that time. These omega minus were not there, and they were struggled to form some particular multiplex structure, because only this much you are having. So it will not form that multiplex structure correctly. Then some unknown particle should be here at the end of this particular decouplet. Then they said that there can be one more particle, which is the omega minus. And later in 1963, in 1963 only this omega minus particle were discovered, and it was found that all those properties which were predicted by this eightfold way for this particular omega minus particle were exactly the same. Okay, so it was a great success for this eightfold way. The prediction of omega minus in such a way that formation of this decouplet for uh, this particular group of particles. These are the baryonic resonances. Okay, So these delta particles, which are they formed in a decouplet, like this, and there were a missing particle at the end of this decouplet. They were not able to find that particle at that time, and they told that there can be one more particle at the end of this decouplet, and it was later discovered in 1963 with all the properties which were predicted by Gell-Mann and Niemann using this decouplet. So it was a great success story for the eightfold. Okay, so let's wind up this here. We will continue with the cork model in the next